Hello, and welcome to the world of aviation today. Today's lecture is on managing emerging challenges in the aviation industry. I do hope by the end of this lecture, you will have had some basic understanding of how the aviation industry has managed to sustain itself in the midst of growing traffic, shrinking capacity, rising cost of operation, and increased security threats. A very warm welcome to a very special group of people, the young aviators. Since the first propelled flight was made in 1903 by the Wright brothers, which inaugurated the era of air transportation, the aviation industry has experienced an overwhelming growth. But as the industry grew exponentially, so did the challenges, which included propagation limitations of the line-of-sight systems, limitations of voice communication, and a lack of digital air-ground data. A crowded airspace, increased terrorism, runway and ramp capacity, a rising operating costs, rising fuel costs, environmental issues, communicable diseases, and of late, COVID-19, fatigue, both by the pilots and controllers, runway safety, and training. So how did the industry respond to these challenges? Number one, it responded with technology. Secondly, it responded with strong regulation, and especially with standards. It responded with plans, and finally, it responded with oversight. Now, let us explore how the aviation industry has harnessed technology to overcome the challenges posed by its remarkable growth. In the early 1980s, the International Civil Aviation Organization, ICAO, recognized the increasing limitation of the present air navigation systems and the need for improvements to take civil aviation into the 21st century. And so in 1983, ICAO established the Special Committee on Future Air Navigation Systems, which is also known as FANS 1. The need for change in the current global air navigation system is due to two principal factors. The first one being the present and growing air traffic demand, with which the current system, by virtue of its limitations, will be unable to cope. And the second, the need for global consistency in the provision of air traffic services during the progression toward a seamless air traffic management system. Now, the FANS 1 committee concluded that the shortcomings of the present communication, navigation, surveillance system, or CNS, amounted to three factors. The first one being the propagation limitation of the current line of sight systems like surveillance radar, VOR, DME, and the rest. The second, the difficulty caused by a variety of reasons between states to implement present CNS systems and operate them in a consistent manner in large parts of the world. And the third one, the limitations of the voice communications and the lack of digital air-to-ground data interchange systems to support modern automated systems in the air and on the ground. And the committee concluded that the new CNS systems should surmount these limitations to allow air traffic management on a global scale to evolve and become more responsive to users' needs. Therefore, they should provide for global communications, navigation, and surveillance coverage from very low to very high altitudes, also embracing remote, offshore, and oceanic areas. They should also provide for digital data interchange between air and ground systems, and a navigation approach service for runways and other landing areas which need not be equipped with precision landing aids. So this original funds committee completed its tasks in 1988 with a system concept for communication, navigation, and surveillance, commonly known as CNS, based largely on satellites, which would enable the evolution of air traffic management, that is ATM, in a consistent manner. The concept will enable civil aviation worldwide to overcome the well-known shortcomings of the present system and take advantage of modern technologies to meet aviation's projected growth well into the 21st century. So what are some of the problems with the current communication system? The main mode of communication between the pilot and controller is via VHF, the terminal and en route airspace, and via HF in the oceanic airspace. Now, both of these have a capacity, clarity, and interference problems. HF and VHF are frequency resource which is managed and issued by the International Telecommunication Union, also known as ITU. It is a limited resource, and any given state cannot have as many frequencies as they wish for their local services. Also, the frequencies being classified in the same frequency band, the possibility of interference is very high. Now, in order to address some of these problems, the industry has responded with a technology known as VHF data links. And this technology is classified into about 3 or so modules. You have what you call the VDL Mode 2, VDL Mode 3, and VDL Mode 4. For example, with one frequency, VDL Mode 3 is able to create up to 4 discrete digital channels. This will make it possible to have both digital voice and data transmitted via the same frequency hence increasing capacity of the frequency with tremendous improvement on voice clarity and zero interference. So a controller will be able to communicate with a pilot on voice and at the same time send data on the same frequency. Also, with the 4 channels, up to 4 controllers will be able to communicate with 4 pilots on the same frequency at the same time. Please look out for a detailed VDL YouTube lecture in the upcoming videos. The other technology that the industry has introduced under communication is called HDLC, High Level Data Link Control. This is a communication protocol that is used for transmitting data between devices in telecommunication and networking. Another one is Voice over Internet Protocol, or VoIP. Again, this is a technology that is finding its way on the desk of the controller and is increasingly being used to communicate or transmit information between air traffic services units of neighboring states. It is a cheaper way of communicating between the 2 units. The other technology that we want to discuss is the AIDC, Air Traffic Interfacility Data Communication. So the AIDC application automatically exchanges air traffic control information between air traffic service units in support of the air traffic control functions relating to notification of flights approaching an FIR, that is Flight Information Region boundary. Also used for coordinating of boundary crossing conditions and transfer of control at the FIR boundary. Another technology which is becoming increasingly important and finding its way on the display of the controller is the ADS-C, which is Automatic Dependent Surveillance Contract, with an emphasis on CPDLC, which is Controller Pilot Data Link Communication. With CPDLC, the controller is able to communicate with the pilot in oceanic areas and places where otherwise voice communication is a challenge. So it is also increasingly replacing HF in the oceanic. It is an accurate way of communicating and also a safe way of doing so. And finally, under communication, the industry has seen the traditional or conventional flight information service, that is FIS, being increasingly replaced by the data link flight information service, or DFIS. So now, let us see how the industry also responded to the traditional or conventional ground-based navigation system. As discussed earlier, the France 1 committee had recommended the migration of technology towards a satellite-based system, since ground-based systems like the DVOR, DME, ILS, and even the microwave landing system are affected by propagation limitations like line of sight, signal reflections, and weather. There is also the problem of inability to provide a consistent performance throughout the globe. That is to say, there are states or areas with strong ground facilities while others have absolutely none. So the industry has seen a progressive and aggressive shift in terms of technology from ground-based systems to satellite-based ones. And it has seen the introduction of GNSS, which stands for Global Navigation Satellite System, GBAS, Ground-Based Augmentation System, and SBAS, which stands for Satellite-Based Augmentation System. What is GNSS, which stands for Global Navigation Satellite System? It is simply a network of satellites broadcasting timing and orbital information, which is used for navigation and positioning measurement. Examples could be like the GPS, which is the Global Positioning System, and which is American, and the signal is free. You could have also the other example is the EGNOS, which stands for European Geostationary Navigation Overlay System, which is European. And we also have the GLONASS, which stands for Global Navigation Satellite System, which is Russian. However, the GPS has been the most preferred system so far. So the benefit of GNSS in aviation is enabling aircraft to fly direct from departure to destination, using the most fuel-efficient route or to avoid complicated terrain at low altitude. GNSS has enhanced the design of performance-based navigation, PBN routes, and procedures, which are designed to meet a navigation specification which is defined in terms of accuracy, integrity, availability, continuity, and functionality for the proposed operations in the context of a particular airspace. The industry has seen an increased introduction of GNSS procedures all over the world since the introduction of GNSS. And what is GBAS? The GBAS, or Ground-Based Augmentation System, is an all-weather landing system which is based on real-time differential correction of the GPS signal. Local reference receivers send data to a central location at the airport. This data is used to formulate a correction message, which is then transmitted to users by a VHF data link. A receiver on an aircraft uses this information to correct the GPS signal, which then provides a standard ILS type display to use while flying a precision approach. It supports all phases of approach, landing, and departure, and surface operations within its area of coverage. The current instrument landing system, that is ILS, as we have seen, suffers from a number of technical limitations, such as VHF interference, multipath effects, as well as ILS channel limitations. GBAS is expected to play a key role in maintaining existing all-weather operations capability at Cat 1, 2, and 3 airports. The operational benefits of GBAS include one GBAS ground station will be able to support multiple runway ends. Flight inspection and maintenance requirements will be reduced compared to maintenance of ILS. The signal is more stable, the accuracy is improved, safety is increased. By providing better navigation data, GBAS reduces the risk of accidents during approach and landing. It's also cost-effective. It can lower operational cost by reducing the need for expensive ground-based navigation aids. As we have said, one GBAS ground station will be able to support multiple runways. It will also have enhanced capacity. GBAS allows for more efficient use of airspace, enabling higher traffic volumes at airports. It also offers flexibility. It supports various types of aircraft and they can be adapted to different airport environments. And also, and important, it reduces environmental impact. By optimizing flight paths, GBAS can help minimize fuel consumption and emissions. Also, real-time. It provides real-time updates. So GBAS provides real-time corrections to GPS signals, improving reliability during critical phases of flight. It also gives support for advanced procedures. It enables the implementation of advanced approach and departure procedures, enhancing operational efficiency. As for SBAS, that is a satellite-based accommodation system, services provide capabilities to improve location data for normal and more developed global positioning system, that's the GPS devices. The Global Navigation Satellite System, or GNSS, signals received in normal GPS devices can be improved from several meters accuracy to sub-meter accuracy. The SBAS system is a system that improves the precision and accuracy of the GPS signal. It uses a combination of specialized satellites and ground-based stations to send correction signals to GPS receivers, as well as providing integrity information for each satellite signal, thereby improving the accuracy of the GPS signals by approximately 5 times. Without the SBAS, ionospheric disturbances, clock drift or timing, and satellite orbit errors create too much error in the GPS signal for aircraft to perform a precision approach. What is a precision approach? It is the one that is always aligned with the runway. So if you look at the accuracy of these systems, you find that the GBAS can give an accuracy of up to less than 1 meter, thus achieving category 1 ILS accuracy of 16 meters lateral and 4 meters vertical. The goal of the GBAS technology is to provide category 3 ILS capability. This allows aircraft to land with zero visibility. For SBAS, this system has an accuracy of up to less than 3 meters. Now, this accuracy in the horizontal plane is less than 2 meters. So S-bus is capable of achieving Category 1 precision approach accuracy of 16 meters lateral and 4 meters vertical. The standard GPS signal can give an accuracy of less than 10 meters. So we are saying that for GBus, it will be able to control the aircraft right from terminal to approach up to the surface, up to the ground. And that's why it can even be used as in place of the ILS up to Category 3. And for the S-bus, it will be able to control aircraft right from en route, oceanic, and en route domestic. Now, the last area of improvement, as recommended by FANS 1 committee, was surveillance. For many years, the conventional way of monitoring aircraft in the en route airspace has been primary radar and SSR in the approach or terminal airspace. Both primary radar and SSR suffer from line of sight propagation problem. This means in order to cover the whole airspace, several radars are required, making it expensive. So how did the industry respond to this challenge? The industry responded with the introduction of the automatic dependent surveillance broadcast. With this technology, there is no need for the radar systems, and aircraft can be monitored beyond the line of sight. As a matter of fact, it is possible to control aircraft in large areas of airspace, including oceanic areas, where availability of radar services is not possible or extremely expensive. ADS-B is a satellite-based technology that makes it possible to monitor aircraft beyond the line of sight. Now, the FANS committee, which finished its task in 1988 with a system concept for communication, navigation, and surveillance based largely on satellites. It anticipated that this will enable the evolution of air traffic management, also known as ATM. Since then, the aviation industry has seen the progressive shift from air traffic control to air traffic management. Air traffic control focuses largely on the safe and efficient movement of aircraft in controlled airspace, primarily during takeoffs and landing, whereas air traffic management encompasses a broader range of activities, including strategic planning, airspace design, and overall management of air traffic flow. The industry has seen the progressive move of the industry from a fragmented airspace into a seamless airspace. One of the major problems with the current air traffic control system is delays and the congestion in the airspace, which makes air operation expensive for the airlines and frustrating for the travelers. Delays in clearing aircraft for landing because of lack of parking, long queues in migration, and unfriendly security checks has resulted in the industry using modern technology to try and contain the problem. The industry has thus seen the introduction of a seamless airspace, direct routing, collaborative decision-making, continuous descent operation or CDO, continuous climb operation CCO, and air traffic flow management. The industry has also seen the progressive movement of the conventional aeronautical information service to aeronautical information management, or from a product-based services to digital data exchange. The industry has seen the introduction of the electronic aeronautical information publication, the introduction of the electronic terrain and obstacle data, and the introduction of the digital NOTAM. The electronic terrain and obstacle (ETOD) is the digital representation of terrain and obstacles provided as datasets satisfying user requirements for a series of airborne and ground applications. Such an application as the enhanced ground proximity warning system uses ETOD to help flight crews avoid controlled flight into terrain by providing information about terrain and obstacles. ETOD also is increasingly being used for procedure design. As with the digital NOTAM, the digital system will allow pilots to tailor NOTAM searches very specifically to their mission. They no longer have to look through pages of paper to access information. In some states, pilots have to visit the NOTAM office or offices for briefing or NOTAMs. This will not be necessary with the digital NOTAMs. So, we have seen how the industry responded with technology to address the emerging challenges in the aviation industry. But there was still a problem. How do you ensure compliance by the sovereign states in implementing recommended standards? This is where regulation comes in. The industry saw the need for policy guidelines for the orderly development of the domestic and international air transport industry in a healthy and a competitive environment. Accordingly, the Civil Aviation Authority of that particular state has the responsibility to prepare a framework of policy for domestic air transport services, keeping in view the various parameters, namely ensuring safety, security, and orderly growth of air transport services, and keeping in view the infrastructure constraint at a number of airports. And most importantly, domesticate and give force to all ICAO standards, that is SAPs, as contained in the 18, or should we say 19 annexes to the Chicago Convention. That is, if we include the safety annex. Now, the annexes cover all technical and operational aspects of international civil aviation. Standards are specifications, the uniform application of which is necessary for the safety or regularity of international civil aviation. Nonetheless, recommended practice is one agreed to be desirable but not essential. Now, having dealt with the issue of regulation, the industry now looked to the issues of quality of service as a means of enhancing safety. From the airlines, an oversight program known as IOSA, that is IATA Operational Safety Audit, was developed by the International Airline Transport Association, IATA. The program is an internationally recognized and accepted evaluation system designed to assess the operation management and the control systems of an airline. IOSA's quality audit principles are designed to conduct audits in a standardized manner. This is not a mandatory program for the airlines, but it improves the safety of the airline and reduces accidents. The other oversight programs are by ICAO. The first one is the ICAO Universal Safety Oversight Audit Program, USOP. The ultimate goal of the ICAO Universal Safety Oversight Audit Program, USOP, launched in January 1999 in response to widespread concerns about the adequacy of aviation safety oversight around the world, is to promote global aviation safety through the regular auditing of safety oversight systems in all ICAO contracting states. Specifically, the USOP audits focus on the state's capability for providing safety oversight by assessing whether the critical elements of a safety oversight system have been implemented effectively. The audit teams also determine the state's level of implementation of safety, relevant ICAO standards, and recommended practices, SAPs, associated procedures, guideline materials, and practices. The 8 critical elements are as follows. The first one is the primary aviation legislation. So states implement aviation regulations in their national legislation. Such legislations must comply with the provisions of the ICAO Convention of 1944. The second one is specific operating regulations. The third one is state civil aviation and oversight functions. The fourth one is technical personnel qualification and training. The fifth one, technical guidance, tools, and provision of safety critical information. The sixth one is licensing, certification, authorization, and approval obligations. The seventh is surveillance obligations. And finally, the eighth one is resolution of safety concerns. The other audit program by ICAO is a Universal Security Audit Program, USAP. Again, just like the first one, it has 8 critical elements. The first one is aviation security legislation. Second one is aviation security programs and regulations. The third one, state appropriate authority for aviation security and its responsibilities. The fourth one is personnel qualifications and training. The fifth one is provision of technical guidance, tools, and security critical information. The sixth one is certification and approval obligations. The seventh one is quality control obligations. And the eighth one is resolution of security concerns. Now, in order to manage this tremendous growth in the aviation industry, the industry came up with plans through ICAO. So the first of those plans is a Global Aviation Safety Plan, also known as the GASP. The GASP can assist ICAO states and regions in the aviation safety policy, planning, and implementation activities in several ways. Firstly, it sets out the global air navigation safety objectives, including specific milestones and priorities to be addressed by state and regional aviation safety planners. Secondly, it provides a familiar planning framework to assist states and regions to make improvements in safety through the use of the 4 safety performance enablers. That is standardization, collaboration, resources, and safety information exchange. And finally, it outlines implementation strategies and the best practice guidance material to assist states and regions in their efforts to tailor state and regional solutions to address the global objectives and priorities. The second plan is a Global Air Navigation Plan, also known as the GANP. The Global Air Navigation Plan, GANP, outlines strategic approaches for the implementation of new technologies in air navigation. Its primary goal is to enhance efficiency, safety, and environmental sustainability by improving capacity and reducing operational costs. By introducing innovative solutions, the GANP aims to optimize air traffic management systems and streamline operations across the globe. And finally, we look at the ICAO Global Aviation Security Plan, or GASEP. This plan addresses the needs of states and the industry in guiding all aviation security enhancement efforts through a set of internationally agreed priority actions, tasks, and targets. We shall be talking more about each of these plans in detail in subsequent YouTube lectures. So, after finding solutions to the problems that arose with the expansion of the aviation industry, there arose the challenge of implementing the new technologies. So with every new technology, the airlines had to grapple with the issue of retrofitting of new equipment into the dashboard of the aircraft. Also, training on the new technologies. Training of users to be able to use new technologies on the desk and the cockpit is a big challenge. The users also need to be certified to use the new equipment. This has slowed down the implementation of the new technologies in many countries. There are also regulatory issues and certification. So when it comes to regulatory issues, any new technology that a state introduces must have procedures that have to be approved by the regulator. This may cause unplanned delays in deploying new technologies in given states where the regulator is not ready to certify the use of the new technology. The other one is the retirement of conventional equipment like radars, VRs, DMEs, ILS. So the retirement of this conventional equipment is also a challenge where a state has just invested a lot of money to install them. Normally, the lifespan of electronic equipment is about 12 years, and it may not be cost effective to retire equipment that is still providing good and useful service. Also, a number of countries have been shy in embracing new technology for fear of not being able to fully control the satellite signal supplied by another state. They feel vulnerable politically. In order to overcome most of the implementation challenges which we discussed earlier, ICAO has come up with an aggressive implementation program called the Aviation System Block Upgrade, also referred to as ASBU. What is an aviation system block upgrade? The program designates a set of improvements that can be implemented globally from a defined point in time to enhance the performance of the ATM system. It comprises a suite of modules, each having the following essential qualities: a clearly defined, measurable operational improvement and success metric, necessary equipment and/or system in aircraft and on the ground along with an operational approval or certification plan, standards and procedures for both airborne and ground systems, and a positive business case over a clearly defined period of time. So as an example, let's look at the modules which were supposed to be implemented in Block 0. Block 0 was originally supposed to start being implemented from the year 2013 onward. Block 1 modules were scheduled to start being implemented from 2019 onwards. Block 2 from 2023 onwards, and lastly Block 3 from 2028. So the area of improvements in Block 0 The first one was airport operations. And in this area of improvement, there were 5 modules which were to be implemented. The first one was a optimization of approach procedures. The second one was increased runway throughput through wake turbulence separation. The third one was improved traffic flow through runway sequencing. The fourth one was safety and efficiency of surface operations. And the fifth one was improved airport operation through airport collaborative decision making. The aim of this improvement was to come up with what we call an integrated arrival manager, departure manager, surface manager operation. We call it AMAN, DMAN, or SMAN. Now, this is an integrated sequencing tool that optimizes runway throughput while achieving smooth aircraft traffic flows through the airport under nominal conditions. The second area of improvement in Block 0 is the globally interoperable systems and data. And the modules which were to be implemented in this performance area, number one is the digital aeronautical information management. The second one is increased interoperability, efficiency, and capacity. While the third one is the meteorological information supporting enhanced operation. So the outcome of this was to provide flight and flow information for a collaborative environment. The third area of performance improvement in Block 0 was optimum capacity and flexible flights. In this area, 7 modules were to be implemented. The first one, improved flow performance through network planning. Second one, improved operations through enhanced en route trajectories or trajectories. The third one, initial capability for ground surveillance. The fourth one, air traffic situational awareness. The fifth one, improved access to optimum flight levels. The fifth one was the ACAS improvements. And the seventh one was increased effectiveness of ground-based safety nets. So the outcome of this was to be able to manage the traffic complexity management. The final area of improvement or performance improvement in Block 0 was the efficient flight path, which had 3 modules. The first one, initial application of data link en route. The second one, improved flexibility and efficiency in descent profile. And the last one, improved flexibility and efficiency in departure profiles. The output of this was to achieve a full 4D or four-dimensional trajectory. That is 3D plus time. Now, to summarize what we have just said, the performance improvement areas in the first area of airport operations will mainly depend on GNSS-based approaches, better wake vortex minima, advanced surface movement guidance and control system, airport collaboration decision-making, and improved metering. And the globally interoperable system and data modules, the three modules that we have just discussed, will mainly depend on ground-to-ground integration based on AIDC, which we saw earlier, digital aim, and other developments. And in the area of optimum capacity and flexible flights, they will depend on, the 7 modules will be basically on performance-based navigation, PBN, flexible use of airspace, FUA, and CDM, collaborative decision-making in combination, improved flow planning, and air traffic situational awareness. And finally, in the area of efficient flight path, the modules will be based on the existing data link operations which support continuous descent operations, continuous climb operations, and en route operations. In conclusion, the response by the industry in responding to the emerging challenges cited in this lecture have resulted in greater capacity for the industry, fewer delays, reduced environmental impact, improved safety, improved security, and the cost effectiveness of operations across the industry. Thank you for staying with me until the end of this lecture. I hope you now have some basic understanding on how the industry continue to address the challenges that arise with the expansion of the aviation industry. If you are a student and wish to share this video with others, kindly feel free to do so. Let us meet at the next video. Thank you.